The mysterious planets in the universe are not only symbols of wonder but also harbor conditions that far surpass the limits of survival known to humanity. Among them, DR2b, 55 Cancri E, and Kepler 70b are three standout planets with astonishingly extreme environments. DR2b, also known as TRES 2b, is a gas giant planet located in the Draco constellation, approximately 718 light-years from Earth. Discovered in 2006 thanks to significant advancements in space telescopes, this planet quickly drew attention for its extraordinary light-absorbing properties. Dubbed the darkest planet in the universe, DR2b absorbs over 99% of the light from its host star. This is not only an astronomical marvel, but also a fascinating research subject, raising numerous questions about the composition and evolution of exoplanets. Unlike typical planets that reflect some portion of light, DR2b's surface appears to absorb all light directed at it. Observed from a distance, the planet resembles an almost entirely invisible black mass, detectable only by its gravitational effects on nearby light and objects. However, this absolute darkness does not imply a cold planet. On the contrary, DR2b's surface temperature reaches an astonishing 1,000 degrees Celsius, 1,832 degrees Fahrenheit, enough to heat and redden its upper atmospheric layers. The faint red glow emitted by the planet gives it the appearance of a smoldering ember, creating a stark contrast between its dark, desolate exterior and its intense internal heat. Why does DR2b possess such an incredible ability to absorb light? The answer lies in its unique atmospheric composition and structure. Studies suggest that DR2b's atmosphere may contain unusual chemical compounds never before observed on other planets. These compounds are capable of absorbing most wavelengths of light, rendering the planet nearly non-reflective. Some theories propose that specific chemical reactions within DR2b's atmosphere contribute to its nature as a natural black hole of light. This discovery holds immense potential, opening doors to studies in chemistry and physics within extreme environments. In addition to its light-absorbing properties, DR2b's position also plays a crucial role in shaping its characteristics. The planet orbits very close to its host star, a yellow dwarf similar to the Sun. This proximity subjects DR2b to intense radiation and heat emitted by the star. This not only heats the planet's surface, but also helps maintain high atmospheric temperatures. DR2b is also tidally locked, meaning one side of the planet always faces the star while the other remains in perpetual darkness. This temperature polarization adds complexity to its atmospheric structure and creates ultra-strong wind currents sweeping across the planet. Despite DR2b's extreme environment, it is not considered the most dangerous planet in the universe. Instead, DR2b is likened to a natural laboratory for scientists to study how gas giants form and persist under adverse conditions. Specifically, studying DR2b can provide valuable insights into the evolution of star systems and the survival of planets in extreme environments. This data is not only valuable for understanding DR2b, but also offers potential discoveries about similar planets, even those that might support life in the universe. This enigmatic planet also raises intriguing questions about the role of light and heat in sustaining life on planets. While DR2b cannot support life as we know it, studying its characteristics can help scientists better understand the conditions necessary for a planet to support life. If DR2b, a planet that absorbs nearly all light and endures extreme temperatures, can exist stably, the survival of other planets in similarly harsh environments may not be impossible. Overall, DR2b is not just an astronomical wonder, but a testament to the diversity and complexity of exoplanets. It broadens humanity's perspective of the universe, while reminding us that star systems out there may harbor mysteries far beyond imagination. DR2b symbolizes both the wonder and the challenges the universe poses to humankind. A relentless journey to explore and understand our place in the vast cosmos. 55 Cancri E, one of the most fascinating exoplanets ever discovered, lies approximately 41 light-years from Earth in the Cancer constellation. This rocky planet, with a mass 8 times that of Earth, is a unique testament to the diversity of worlds beyond our solar system. What makes 55 Cancri E particularly special is its carbon-rich composition, a rare feature in planetary systems like ours. Due to this composition and its extreme surface temperature, scientists have hypothesized that the core of 55 Cancri E may contain massive layers of diamonds, earning it the nickname Diamond Planet. One of the most remarkable features of 55 Cancri E is its ultra-short orbit. The planet takes only about 18 hours to complete one revolution around its host star, a sun-like but brighter and hotter star. This results in tidal locking, where one side of the planet always faces the star while the other remains in perpetual darkness. This phenomenon creates a stark temperature contrast between the two hemispheres, with the day side scorching hot and the night side relatively cooler, but still too unstable for equilibrium. Temperatures on 55 Cancri E's day side reach a staggering 2,400 degrees Celsius, 4,352 degrees Fahrenheit, hot enough to vaporize most light elements. Its surface is believed to be covered in molten lava and ash, creating a chaotic and inhospitable scene. Conversely, the night side, while cooler, remains insufficiently cold to stabilize conditions. The lower temperature on the night side primarily results from the lack of starlight, but the difference is not enough to induce significant convection or strong thermal movements between the two sides. Consequently, 55 Cancri E lacks a stable atmosphere, making its environment harsher than ever. The chemical composition of 55 Cancri E is a captivating aspect for scientists. With an abundance of carbon, the planet may host large diamond layers in its core. Diamond formation could be driven by extreme pressure at the planet's core, combined with prolonged high temperatures. This hypothesis not only fuels curiosity about the planet, but also raises questions about the existence of other carbon-rich planets in the universe. If 55 Cancri E indeed contains a significant amount of diamonds, it represents a type of planet entirely distinct from the rocky worlds familiar to us in our solar system. In addition to being a gem in the field of astronomical discovery, 55 Cancri E offers an opportunity to study the evolution of planets in extreme environments. The survival of a planet under such intense temperature and pressure conditions prompts questions about its durability and structure. This also provides critical information about how carbon-rich planets form and persist, shedding light on the diversity of planetary compositions and structures in the universe. Studying 55 Cancri EA not only helps scientists understand extreme conditions, but also opens the door to potential discoveries about life and unique environments in the cosmos. Although not a candidate for life as we know it, this planet offers a new perspective on how chemical and physical factors can shape distant worlds. It also raises significant questions about carbon's role in forming planets and the potential development of other carbon-rich environments. Overall, 55 Cancri E is not just an astronomical marvel, but an endless source of inspiration for scientists. From its lava-covered surface to the potential diamond core, this planet clearly demonstrates the universe's wonder and richness. While direct access to 55 Cancri E remains unattainable in the near future, research and observations will continue to unveil its secrets, providing deeper insights into humanity's place in the vast cosmos. Kepler 70b, formerly known as KOI 55b, is one of the most unique and extreme exoplanets ever discovered. Situated extremely close to its host star, the planet's surface temperature reaches 6,800 degrees Celsius, 12,272 degrees Fahrenheit, hotter than the Sun's surface temperature of approximately 5,500 degrees Celsius, 9,932 degrees Fahrenheit. This proximity not only makes Kepler 70b a fiery inferno with some of the harshest environmental conditions, but also renders it a fascinating research target, raising questions about the survivability of planets under extreme conditions. One of Kepler 70b's most distinctive features is its ultra-short orbital period. The planet takes only about 345 minutes, or 6 hours, to complete one revolution around its host star, making it one of the fastest orbiting planets known. This close proximity subjects Kepler 70b to intense heat and radiation, continuously melting its surface material and causing near-total evaporation of any matter on its surface. This closeness not only elevates temperatures, but also generates unusual physical conditions, making the planet a prime example of the harshness of the cosmic environment. Scientists believe that Kepler 70b was not always a planet. Instead, it may have once been part of its host star before undergoing a dramatic transformation. As the host star approached the end of its life cycle, it may have undergone a supernova explosion or collapsed into a white dwarf. During this process, the outer layers of the star were expelled, leaving behind smaller remnants, some of which may have condensed into Kepler 70b. This process not only altered the planet's structure and composition, but also transformed it into a smoldering remnant of its host star, characterized by its exceptionally harsh conditions. Kepler 70b's surface is not only exposed to extreme temperatures, but also heavily impacted by radiation and unique physical processes. Metals on its surface are vaporized by the intense heat, dispersed into space, and potentially recondensed into layers of exotic materials. These layers may contain unstable chemical compounds, adding further complexity to the planet's nature. The continuous evaporation and condensation processes create a harsh chemical ecosystem, making Kepler 70b a natural laboratory for studying interactions between stellar radiation and planetary matter. This planet also raises critical questions about the survivability of planets in extreme environments. The fact that Kepler 70b can exist and maintain its orbit under such conditions is a testament to the resilience of planetary structures. Simultaneously, it prompts inquiries into how planets form and evolve after their host stars undergo dramatic changes, like supernovae or white dwarf formation. Kepler 70b also exemplifies the incredible diversity of exoplanets. From its molten surface to its unique formation history, the planet illustrates the universe's capacity to create worlds with environmental conditions and structures far beyond human imagination. Research strange planets in the universe captivate us not only with their mysterious appearances, but also with their unimaginably extreme conditions, from hellish temperatures, supersonic winds, to sharp glass rainstorms. These are worlds so extraordinary that even science fiction struggles to conceive of them. Temperature and extreme conditions. Temperature is one of the most critical factors shaping the harshness of exoplanets, and nowhere is this more evident than in worlds like DR2b, 55 Cancri e, and Kepler 70b. These planets are not only distinct in structure and orbit, but also challenge every known boundary of environmental conditions. Each is a vivid example of how extreme temperatures can define and entirely transform their landscapes and habitability. DR2b, also known as TRES-2b, is a gas giant located 718 light-years from Earth, with a surface temperature of approximately 1,000 degrees Celsius, 1,832 degrees Fahrenheit. This level of heat is sufficient to melt most lightweight metals, leaving its surface in a state of intense searing heat. Remarkably, despite being cloaked in near-total darkness due to its absorption of over 99% of light from its host star, DR2b emits a faint red glow from internal heat. The image of DR2b evokes a stark contrast, a pitch-black orb glowing like a perpetual furnace in the cold expanse of space. This planet is not only an astronomical marvel, but also an intriguing research subject that helps scientists better understand how planets survive under extreme conditions. 55 Cancri e, located about 41 light-years from Earth, presents another level of extremity, with daytime surface temperatures soaring to 2,400 degrees Celsius, 4,352 degrees Fahrenheit, one of the highest temperatures ever recorded. At such heat, most chemical compounds vaporize, leaving its surface covered in bubbling lava and ash. However, what sets 55 Cancri e apart is not just its temperature, but also its chemical composition. Scientists believe the planet's surface may contain large amounts of pure carbon, creating conditions that could form diamonds in its core. This transforms 55 Cancri e into a giant diamond in the universe, where heat and pressure have entirely redefined its structure. Kepler 70b, previously known as KOY 55b, takes the concept of extreme temperatures to another level. With a surface temperature reaching 6,800 degrees Celsius, 12,272 degrees Fahrenheit, Kepler 70b is even hotter than the Sun's surface, a seemingly impossible feat for a planet. Its proximity to its host star exposes it to not only extreme temperatures, but also intense radiation, continuously melting its surface. Under such harsh conditions, all complex matter is obliterated, leaving only the simplest materials. Kepler 70b is truly a cosmic furnace, where the existence of any form of life, no matter how primitive, becomes utterly impossible. These planets not only demonstrate the destructive power of temperature, but also highlight the incredible diversity of worlds beyond our solar system. DR2b, with its darkness and faint red glow, 55 Cancri e, with its diamond heart, and Kepler 70b, with its unparalleled temperatures, all showcase how the universe can craft worlds beyond human imagination. Although they cannot support life, they serve as natural laboratories where scientists can study how temperature, pressure, and radiation shape the structure and evolution of planets. In summary, extreme temperatures are not merely a harsh feature, but a defining element of these planets' unique natures. Although direct exploration is impossible, studying them remotely expands humanity's understanding of the universe's diversity. These worlds, with temperatures far exceeding the endurance of any known life, remain crucial to deciphering the fundamental laws of astronomy, reminding us that the universe constantly challenges our imagination and knowledge. Supersonic winds and extreme weather. Powerful winds and extreme weather make many horrifying planets unimaginably harsh worlds. Beyond their scorching temperatures, these planets face violent and unpredictable atmospheric phenomena, creating an environment uninhabitable for any form of life we know. Among them, 55 Cancri A and HD 189733b are prime examples, illustrating the destructive force of these atmospheric conditions. 55 Cancri E, located about 41 light-years from Earth, draws attention not only for its high surface temperatures of 2,400 degrees Celsius, 4,352 degrees Fahrenheit, but also for its unique and hazardous atmosphere. Its atmosphere is filled with hydrogen and helium, gases that are not only highly flammable, but also extremely toxic. Carbon dust clouds blanket the sky, adding an ominous and threatening ambiance. However, these features are just the tip of the iceberg. What truly terrifies about 55 Cancri E is its supersonic winds, which can reach thousands of kilometers per hour. These massive winds are strong enough to blow away all matter on the surface, creating a constantly chaotic and ever-changing environment. The ferocity of these winds on 55 Cancri E is amplified by various factors. Its close proximity to its host star subjects the planet to intense gravitational and radiation forces, increasing the speed and intensity of the gas flows. These winds travel at supersonic speeds, capable of sweeping everything in their path. They can even generate massive cyclones, many times larger than any weather phenomenon observed on Earth. These extreme conditions not only destabilize the planet's surface, but also deeply impact the atmospheric chemistry, altering the composition and properties of the gases. Another example of planetary wind power can be found on HD 189733b, a gas giant located about 64 light-years from Earth. This planet is renowned for its wind speeds of up to 8,700 kilometers per hour, 5,400 miles per hour, 7 times the speed of sound. These ferocious winds tear through the atmosphere, creating unprecedented weather phenomena. They can carry molten silicate particles, producing horizontal glass rainstorms that defy all conventional understanding of weather. The harshness of HD 189733bi makes it one of the most dangerous planets ever discovered, while raising questions about how such worlds can persist in the universe. These extreme atmospheric conditions not only make planets like 55 Cancri E and HD 189733b exceptional, but also provide vital data for studying the formation and evolution of planetary systems. Supersonic winds and unusual meteorological phenomena help scientists better understand how factors like stellar radiation, gravity, and chemical structures interact to create such extreme environments. At the same time, they raise significant questions about the limits of atmospheric physics and the survivability of planets in conditions beyond human comprehension. Overall, powerful winds and extreme weather are key factors shaping the harshness of many exoplanets. Supersonic winds, massive cyclones, and bizarre weather phenomena not only render these planets uninhabitable, but also challenge human imagination and understanding. Studying them not only enhances our knowledge of the universe, but also reminds us that beyond Earth's hospitable environment, countless worlds exist with conditions far beyond the endurance of any known life. Glass and metal rainstorms. If supersonic winds paint a picture of harshness, molten glass and metal rainstorms elevate the terror of exoplanets to an entirely new level. Among them, HD 189733b stands out as a prime example, where the weather not only defies imagination, but also challenges every natural law we are familiar with on Earth. HD 189733b, located about 64 light-years from Earth, is a gas giant with uniquely harsh atmospheric conditions. High temperatures, combined with supersonic wind speeds of up to 8,700 kilometers per hour, 5,400 miles per hour, create a spectacular phenomenon. molten glass rain traveling sideways at dizzying speeds. Unlike ordinary rain on Earth, which falls straight down due to gravity, the glass particles on HD 189733b are swept horizontally by terrifyingly strong winds, producing a dazzling but deadly light show. When starlight reflects off the glass particles, it creates a brilliant blue hue that envelops the entire planet, turning HD 189733b into a radiant sapphire in the cosmos, but one fraught with peril. These glass rains are not only a rare phenomenon, but also catastrophic for any material daring to exist on the surface. The high temperatures and intense winds are powerful enough to crush or melt any physical structure, making HD 189733b a world where physical stability is nearly impossible. Yet, these extreme conditions provide a unique opportunity to study how planets survive and evolve in harsh environments. Beyond glass rain, some planets, such as WASP 121b, experience metal rainstorms, adding to the diversity and severity of exoplanet weather. On these planets, temperatures are so high that metals like aluminum or titanium vaporize and mix into the atmosphere. When temperatures drop slightly in higher atmospheric layers, these metals condense into droplets, falling back to the surface as rain. These metal droplets not only alter the planet's surface, but also create a gleaming metallic layer, akin to a dazzling suit of armor. However, this armor is not a symbol of protection, but a testament to the planet's insurmountable harshness. Metal and glass rainstorms affect more than just the surface. They profoundly influence atmospheric chemistry. The interactions between rain particles and the atmosphere create a volatile environment where chemical reactions continuously occur. These changes not only shape the atmospheric structure, but also raise significant questions about how factors like temperature, pressure, and stellar radiation define planets. These phenomena provide scientists with a unique chance to study unfamiliar environmental conditions and understand the complexity and diversity of exoplanets. Besides HD 189733b and WASP 121b, many other planets in the universe likely harbor unimaginable weather phenomena. Each world serves as a natural laboratory, expanding our understanding of physical and chemical laws beyond Earth. Glass and metal rainstorms demonstrate not only the extraordinary adaptability of planets, but also the boundless creativity of the universe. In conclusion, molten glass and metal rainstorms highlight the harshness of planets, like HD 189733be, while emphasizing the endless diversity of distant worlds. These are not only visually stunning phenomena, but also a reminder that the universe is filled with mysteries and challenges far beyond human imagination. These discoveries continue to open new frontiers in research and understanding of the vast cosmos, where the impossible becomes reality. Horrifying planets. How can humans, from a tiny planet like Earth, observe and discover distant worlds hundreds or even thousands of light years away? The answer lies in the combination of modern technology, advanced data, and boundless scientific imagination. Modern technology and space telescopes. Modern technology has revolutionized the exploration of the universe, especially in the quest to find and study exoplanets. Advanced tools like the Kepler and Hubble space telescopes have become indispensable in helping us understand distant and extreme worlds, opening new horizons in astronomy. Launched in 2009, the Kepler Space Telescope was one of the pioneering missions specifically designed to search for exoplanets. Its mission focused on detecting planets using the transit method, which involves monitoring the dimming of starlight, when a planet passes in front of its host star. This technique, while simple in principle, has been incredibly effective, leading to the discovery of thousands of exoplanets. Among these are extreme and peculiar worlds like Kepler 70b, a fire planet with surface temperatures reaching 6,800 degrees Celsius, 12,272 degrees Fahrenheit. Thanks to Kepler, we have not only confirmed the existence of these planets, but also gathered valuable data about their sizes, orbits, and distances from their host stars. While Kepler focused on discovering a large number of planets, the Hubble Space Telescope has elevated our understanding by providing detailed observations of specific exoplanets. With its advanced imaging and spectroscopic capabilities, Hubble has allowed scientists to study the atmospheric compositions of planets, like HD 189733b. One of Hubble's most remarkable findings is the phenomenon of glass rain on HD 189733b, a weather condition never observed before. By analyzing light reflected from the planet's atmosphere, Hubble revealed that it contains molten silicate particles, creating horizontal glass rainstorms at supersonic speeds. Discoveries like this not only broaden our understanding of the universe, but also raise significant questions about how planets endure such extreme environments. In addition to space telescopes, modern technology has introduced advanced methods such as Doppler spectroscopy, a vital tool for detecting and studying exoplanets. This technique tracks the subtle wobbles of a star caused by the gravitational pull of orbiting planets. Instead of directly observing the planets, scientists infer their presence by measuring shifts in the star's light frequency. Using Doppler spectroscopy, astronomers have discovered many massive planets with close-in orbits, such as 55 Cancri e. This planet, with a daytime surface temperature of 2,400 degrees Celsius, 4,352 degrees Fahrenheit, and the potential for pure carbon deposits, vividly illustrates the harshness of exoplanetary worlds. Doppler spectroscopy not only helps locate planets, but also provides detailed information about their masses, orbits, and effects on their host stars. The advancements in technology do not stop here. New generations of telescopes like the James Webb Space Telescope, JWST, are continuing the missions of Kepler and Hubble, offering unprecedented observation capabilities. With its infrared spectroscopic analysis, JWST promises to provide precise information about the atmospheric compositions, temperatures, and surface structures of distant planets. This technology will help us answer critical questions about the potential for life on exoplanets and how they form under extreme conditions. Overall, telescopes and modern technology are not just tools for exploring the universe. They are windows into new understandings of distant planets. From discovering thousands of planets with Kepler, analyzing atmospheric details with Hubble, to pinpointing planets through Doppler spectroscopy, we are witnessing a golden age of astronomy. These technologies not only expand human knowledge, but also remind us that the vast universe holds countless secrets waiting to be uncovered. The role of space data and simulations. Data from space telescopes and scientific simulations play an essential role in exploring and understanding exoplanets. Beyond remote observations, these modern tools provide detailed information, enabling scientists to decipher the extreme and mysterious conditions of worlds outside the solar system. From measuring orbits and temperatures to analyzing atmospheric compositions, data from satellites and simulations have revolutionized our approach to the cosmos. A prime example is the Spitzer Space Telescope, a pioneer in studying distant planets. Spitzer provided valuable data on the extreme temperature differences between the day and night sides of 55 Cancri e, a harsh, rocky planet 41 light-years from Earth. with daytime temperatures reaching 2,400 degrees Celsius and significantly cooler night temperatures. Spitzer's data shed light on the planet's severity while revealing how its atmosphere interacts with its surface. This information helps scientists better visualize the structure and dynamics of carbon-rich planets, opening new avenues for studying exoplanetary atmospheres and surfaces. In addition to real data from satellites, scientific simulations are indispensable for recreating and studying the conditions these planets endure. Using supercomputers and complex algorithms, scientists can replicate phenomena such as supersonic winds on 55 Cancri E or surface melting at 6,800 degrees Celsius on Kepler 70b. These simulations are not just visual. They also provide specific physical parameters, offering deeper insights into how matter reacts and survives in extreme environments. For instance, simulations of high-speed winds on 55 Cancri E have allowed scientists to determine how gas flows influence the atmosphere and surface, creating a more comprehensive picture of this dynamic world. Simulations also predict the future of these planets. One notable example is WASP-12b, a gas giant approximately 870 light-years from Earth. Based on simulations, scientists discovered that WASP-12b is gradually losing its atmosphere at an alarming rate, primarily due to the strong gravitational and radiation forces from its host star. Calculations suggest that this planet may be entirely devoured by its star within a few million years. Such predictions not only offer new perspectives on planetary evolution, but also help identify factors that influence their survival in adverse conditions. Moreover, scientific simulations allow us to test the limits of matter in extreme environments. For example, when recreating conditions on Kepler 70b, scientists found that many chemical compounds stable on Earth cannot survive in temperatures hotter than the Sun's surface. These experiments not only shape our understanding of planetary chemistry, but also provide insights into how planets form and maintain structure in harsh conditions. Data from satellites and scientific simulations are not merely exploration tools, but bridges between theory and reality, bringing us closer to understanding the vast universe. Thanks to these advances, scientists can not only observe and study, but also predict and test hypotheses about the evolution and survival of distant planets. This demonstrates the power of modern technology in unraveling the mysteries of the universe, opening the door to unlimited discoveries in the future. Contributions to planetary science. Studying extreme planets is not just a journey to satisfy humanity's endless curiosity about the universe, but also a critical contribution to planetary science. Worlds like Kepler 70b, HD 189733b, and 55 Cancri E, with conditions far exceeding any known limits, have become natural laboratories, providing valuable data to expand our understanding of natural laws, planetary structures, and even the potential survival of life in extreme environments. One of the most significant contributions of studying these planets is expanding our knowledge of the limits of life. On Earth, extremophiles, organisms that survive in seemingly impossible conditions like high temperatures, immense pressure, or oxygen-deprived environments, exist. However, the conditions on planets like Kepler 70b or HD 189733b far surpass imagination, with temperatures of thousands of degrees Celsius and supersonic winds. Although these planets appear incapable of supporting any life as we know it, they still offer important clues about how life, if it exists, could adapt to various harsh environments. Such studies open possibilities for seeking life beyond the solar system in conditions previously deemed impossible. Beyond exploring life's potential, extreme planets help define criteria for finding Earth-like worlds. By analyzing how harsh conditions like temperature, pressure, and radiation impact planetary structure and atmosphere, scientists can identify factors essential for supporting life. For instance, 55 Cancri E, a carbon-rich rocky planet, may not be suitable for life, but offers insights into how rocky planets form and evolve. This is particularly crucial in searching for other Earths in the universe where conditions might favor life. Additionally, studying extreme planets provides insights into how planets interact with their host stars, offering a better understanding of factors leading to the stability or instability of planetary systems. HD 1897-33b, with an atmosphere filled with silicates and glass rainstorms, has provided valuable data on how temperature and strong winds influence atmospheric composition and surface conditions. This information not only enhances our understanding of planets in the universe, but also helps predict similar phenomena within our solar system. Besides scientific benefits, researching extreme planets prepares us for future space exploration. With new generations of telescopes like the James Webb Space Telescope, JWST, we will gain the capability to observe and analyze these distant planets in greater detail. JWST, with its advanced infrared spectroscopic capabilities, will enable the study of atmospheric compositions, temperature structures, and chemistry of planets. This will provide a more comprehensive view of the diversity of worlds out there and expand the search for planets with potential for life. Finally, this research is a crucial stepping stone for deeper space exploration. Insights gained from extreme planets will better prepare us for missions to distant planets or the search for new astronomical resources. Understanding how planets survive and evolve in extreme environments is not just a scientific achievement, but a key to humanity's future as we venture further into the cosmos. In conclusion, researching extreme planets not only broadens our understanding of the universe, but also lays the foundation for advancements in planetary science, space technology, and the survival of humanity in new environments. These worlds, though alien and hostile, serve as a bridge bringing us closer to answers about life and our place in the vast universe.